Dear students, hope you are doing good. In this session, we are going to see about introduction of power system analysis and some of the topics from the first unit. The electricity is the most convenient form of energy than any other type of energy because it has some advantages over any other type of energy. Here, this electricity can be transmitted over a long distance with reduced loss, and also it can be converted into any form of energy whenever required. For example, so you can convert electric energy into a light or sound or into a mechanical energy, etc. So we are interested to generate electricity and we are utilizing for various purposes. Next, for a generation of electricity, there are number of sources. But according to law of conservation of energy, the energy cannot be generated or destroyed, but we can convert one type of energy into another type of energy so that for converting some sources into electrical energy, these sources are classified in general. There are two types. One is renewable energy sources and another one is non-renewable energy sources. The source may be of any type or the power plant for producing the electricity may be of any type. They are located away from the load center. Load center means it is the area of utilization. That is maybe a city or industrial, but they are located just away from the power plants. The power plants are located where the sources are available. For example, hydro power plant which is located near a dam, and also the thermal power plant which are located away from the city to maintain the problems due to pollution, as well as they are located where the water resources are available. So this generated electricity should be transmitted to load center for utilizing it. Next, the power system. The power system is a very complex network in which number of equipments are connected together to generate, transmit, and distribute electricity. So this collection of equipments are called as power system. As already told, the electric energy is generated, that is converted from these sources already we have seen, and this converted or generated energy should be transmitted, and this transmitted energy is distributed for utilization purpose. So the major areas of power system are: one is generation. In generation, the major equipment used is generator, and second major area is transmission. In this transmission, the major equipments are step-up power transformer along with transmission line, and at the receiving end there is a step-down transformer which is also a power transformer, and third area is distribution. This area consists of equipments like distribution lines, distribution feeders, and distribution transformers. Finally, the utilization. Utilization nothing but which represents the loads. It may be industrial load or domestic load where the power is utilized. Next, power system analysis is the evaluation of power system data. Power system analysis is nothing but evaluation of power system data. This results from this power system analysis used to maintain the power system to be reliable, safe, and to ensure the economical energy distribution to the consumer, as well as to maintain the power system stability. The power system should be stable under any conditions so that to ensure the energy distribution as well as to meet the demand. So this power system analysis results will help for these functions of power system. There are number of power system analysis in which the most important types of power system analysis are: 1. Load flow or power flow analysis, which is concentrated in the second unit. The load flow or power flow analysis is carried out under normal condition of the power system, which will give the information about the power which flows from the generating station to the load, that is up to the area of utilization, consumer up to end user. And also this will give load flow analysis will give the power flow between the buses as well as losses in the transmission line during normal operation of the power system. Next, second analysis, it is short circuit analysis. This short circuit analysis gives the results to design the circuit breaker and protective schemes. The circuit breaker and the protective schemes ensure the protection of this power system under abnormal conditions. For example, if there is any fault in any part of a power system, that should be cleared as soon as possible, or that part should be disconnected from the healthy part as soon as possible. So for ensuring this, there should be some protective device installed. The protective designs are rated based on the short circuit analysis results. The short circuit analysis is concentrated in Unit 3 and Unit 4. Next, stability analysis. This stability analysis gives the results to maintain the power system stability under large and small disturbance like switching transients and change of load and some external causes. Next, the function of power system analysis. As already told, there are number of power system analysis in which we are getting some of the results. So these results will help to do these following functions. One is to monitor bus voltages, real and reactive power flow between the buses, as already told. And second, design of the circuit breakers. And third, plan for a future expansion of a plant or a unit to meet upcoming demand. That is future demand. Next, fourth, to maintain the stability under disturbance, as already told. Next, we will move on to next topic, that is Unit 1, Power System. This unit will give introduction, just a introduction for a power system. As already told, starting from second unit up to fifth unit, there is some analysis. This analysis needs some basic knowledge about power system network, and their simplification we need some basic knowledge. So these basics are concentrated in the first unit. The most important part in which you'll have some part B questions. There, per unit reactance diagram or per unit analysis. Compulsory you'll have one part B question from this per unit reactance diagram. And bus admittance matrix as well as bus impedance matrix. So you'll get one questions from any two of these topics. That is from either bus admittance matrix or bus impedance matrix. So remaining these are some basics need for power system planning and operational studies, etc. Just you'll have some 2 marks from these topics. Let us move on to first unit. Already we have discussed these topics, need for power system planning or operational studies, etc. So next topic is structure of power system. So this is the general structure of the power system. Here we have one generating station which is used to convert the some form of energy into electric energy, and this generated electricity should be transmitted over a long distance where the load centers are located for distributing into consumers. So this transmission is held at two stages. One is primary transmission and another one is secondary transmission. So this transmission is held at two stages to ensure the economical energy distribution, because in the primary transmission the voltage level is very high, about 220 or above, or from 132 and above. So if it is transmitted over a long distance, we need to spend more money on productive devices. So that will increase the cost of the energy of utilization. So that is to manage these problems as well as the problems insulation, that is insulation problems due to high voltage, this transmission is held at two stages. In the second transmission, the voltage level is reduced, that is stepped down to 33 kV or 66 kV. Similarly, the distribution is held at two stages. One is primary distribution and another one is secondary distribution. In primary distribution, the voltage is stepped down to 11 kV or 6.6 kV. This in this primary distributions, the big consumers are supplied from this primary distributions. Big consumers are nothing but industrial consumers. They are in need of more power, so they are supplied from this primary distribution itself. And after this primary distribution section, this voltage is again stepped down to 400 volt for 3 phase and 230 volt for single phase. But finally, in the secondary distributions, the domestic consumers are supplied. Their voltage level is 400 volt for 3 phase and 230 volt for single phase. So these different stages has different voltage levels. For example, this generation voltage level is either 6.6 kV, 10.5 kV, 11 kV, 30.8 kV and 15.75 kV. In India, most of the generating stations are generating the voltage at 11 kV. And while transmitting this generated electricity, the voltage is stepped up to reduce the losses during transmissions. We know that the apparent power, which is given by the product of voltage and current, for a fixed or constant apparent power, while increasing the voltage level, the current will be getting reduced. So with reduced current, we are transmitting the power. With reduced current, the losses will be reduced. That is, I square R losses will be reduced, so that we can increase the efficiency of the transmission. That's why the generated voltage at 11 kV is stepped up to 132 kV or 110 kV or 220 kV or 400 kV or 765 kV. The primary transmission, which is a section between the sending end substation and receiving station. In the receiving station, for example, consider this step-up level, which is stepped up in the sending end substation from 11 kV to 220 kV. So in the receiving stations, The voltage level of received electricity is 220 kV. This 220 kV is stepped down to 33 kV, and the section between the receiving station and the secondary substation is called as secondary transmission. At secondary substation, again the voltage is stepped down to 11 kV or 6.6 kV. After stepping down to this voltage level, the industrial consumers are directly supplied from these secondary substations, and also it is again stepped down after this primary distribution. The primary distribution nothing but which is the section between secondary substation and the distribution station. In distribution station, the voltage is again stepped down to 11 from 11 kV to 400 volt for 3 phase and 230 volt for single phase. From this distribution stations, the domestic consumers are supplied to distribution transformer. These are the general structure of the power system. Next, so we are moving on to next one important topic, that is per unit analysis. So as already I told, there is number of power system analysis. So all those things need some equivalent network of a power system. So these equivalent networks, already as I told, in the power system network there are a number of equipments connected together, and they are also at different voltage level. So if we are using a power system equivalent network with their actual values, that will be very difficult for analysis, because at each level there is change in voltage level. There is at each section there is a change of voltage level. So for using actual values, that is for impedance in terms of ohms, and current in terms of ampere, and voltage in terms of volt, and power in terms of watt, or power in terms of VA. So these are very difficult for analysis purpose. So these actual values are referred from some common base values, some common values. Those values are called as base values. These base values are common throughout the network or some part of the sections. So the actual quantities are replaced with the per unit values. This will make the analysis to be simplified, and it will be very useful for making this analysis computerized manner. So next, we should know what is per unit value. So as already told, the actual values are referred or related with their base values. This per unit value is defined as the ratio between actual value and base value. These values are expressed as a decimal value or in percentage. As the same quantities are that is compared or a ratio, there is no unit for per unit value. So these per unit values are dimensionless. There is no unit for per unit. Simply will represents with P dot Q, that is per unit. Next, so advantages of per unit system. So as already I told, the per unit systems are useful for easy computerized analysis and also for simulation purpose for the power system. We can simply update the values of changes in this per unit system in the computerized analysis. Second, so in the power system network, there is a transformer which changes the voltage level. That is, primary is at different voltage level and secondary is at different voltage level. This will make the analysis to be complex when these analyses are performed with the actual values. So while using per unit system, this complexities are simplified or reduced. Next, so during this analysis, these results will fall in relatively narrow numerical ranges. That means you can easily identify or spot the errors. That is also possible when we are using per unit system. This per unit system gives the relative magnitude information. That means these actual values are related from common base values. So this will gives the relative informations or magnitude informations. And the manufacturers of many equipments it is used in the power system also specifying the ratings with the per unit values. And finally, so while performing the analysis using actual values, we should use root 3 and 3 conversion for converting line voltage into phase voltage or phase voltage into line voltage, and also for calculating three-phase power. So we are in need of this root 3 and 3 conversion, but these conversions are eliminated while using per unit system. So overall, due to these advantages of per unit system, the analysis will be simplified. Next, so we are in need of some more basic knowledge in the per unit values. So as already told, the per unit values are the ratio between the actual values and base values. First, in the per unit voltage, which is the ratio between actual voltage and base voltage. So same quantities will be in the ratio. For example, here the per unit current is expressed as the ratio between actual current and base current. So these similar quantities in the ratios. So which is denoted, this per unit voltage is denoted with the values, sorry, with the letters V. Actual voltage is V, and base voltage is denoted as VB. So B is used in subscript. This B stands for base, and V represents the voltage. So as already told, per unit voltage or per unit values has no unit. So simply they are represented with P dot U, and per unit current, that is equal to I by IB. So IB nothing but this is a base current, and this unit is very dimensional as which is represented P dot U, where VB and IB are base values and they represents the RMS voltage and current respectively. Next, some important relationship between the base values. So already we know that the apparent power is given by the product of voltage and current. So same this relationship can be applicable for base values. Here the base apparent power modulus SB is equal to modulus of VB into modulus of IB. Unit is volt ampere. This SP nothing but base apparent power, so which has unit. The per unit value only has no unit. So base value, so this apparent power has unit volt ampere, and similarly the base impedance. So these base values are obeys Ohm's law. So by using Ohm's law, you can obtain the base impedance value, that is modulus of ZB is equal to modulus of VB divided by modulus of I by IB. So unit of base impedance is ohm. But we have some other forms for base impedance in terms of voltage level, that is base voltage and base MVA. That is very much important for per unit analysis. That is base impedance in terms of voltage, base voltage, and base MVA is much important for per unit analysis. Here I have used red filled circle. This red filled circle means that corresponding formula is very much important for per unit analysis. So you have to keep on remembering these red filled numbered formulas. Next, second, so IB. So base current is equal to, from base apparent power relationship we can write modulus of SB divided by modulus of VB. So from previous base impedance expression, we know that ZB is equal to the ratio between VB and IB. Next, keep this VB and IB as it is and multiply both denominator and numerator with VB. So finally you will get VB square divided by SB. So this base voltage, usually they are expressed in terms of kV, kilovolt. So if we want to submit or substitute this voltage, base voltage in terms of kV, and power also expressed in terms of MVA, megavolt ampere. So we want substitute power in terms of MVA. So while using these powers, that is voltage in kilo and power in mega, this relationship is true. While squaring kilo, you will get 10 power 6. Here in denominator, already the power is expressed in MVA. So here you will have some 110 power 6. Both are will be getting cancelled. So you will get base impedance. So you should keep on remembering this formula. It's a very much important formula. So if you know the base voltage in kV and base apparent power in MVA, so you can calculate base impedance by using this formula. That is KVB square divided by MVA. Next, some per unit values expression, that is apparent power. Already we have seen some apparent power, that is modulus of SP is equal to modulus of VB into modulus of IB. Here these values same apparent power, but the power is expressed in complex form, that is real power plus J reactive power. So same formula will be applicable here, actual power divided by base power, but this S is expressed in complex form. That is the only difference. Here you will have some real part and reactive part. So finally this is in the form of real power per unit plus J reactive power per unit. Here this P subscript P dot U represents the per unit real power, and Q P dot U represents per unit reactive power. So next, apparent power in per unit. This is also another form where this S is replaced with Vi star, which is in the polar form. This is in the polar form. In previous equation, this S is in complex form. So in this second expression, the S is in the polar form. So in polar form, this apparent power is given by V into I star. So finally you'll get V by base voltage and I complex conjugate divided by IB. So finally this apparent power in per unit is equal to V per unit into I per unit complex conjugate. This is in the form of complex form, polar form. This apparent power here expressed in the first equation is in complex form. Next, per unit values expression, some more expressions. Third, so voltage per unit. So already we had an expression for this V by EB. So keep VB as it is and substitute Z into I for V. So simple relationship between voltage, impedance and current. So finally you are getting this relationship. That is, here one modification is there. So in denominator IB is multiplied as well as divided. So after doing this, you can simplify into Z by ZB and I by IB. That is equal to Z per unit into I per unit. That means V per unit is equal to Z per unit into I per unit. From this, what we can conclude that this per unit values also obeys the Ohm's law. That is voltage equal to product of impedance and current. But all these values are in per unit. V per unit is equal to Z per unit into I per unit. And fourth is a very much important formula. You should keep on remembering this. Impedance in per unit, that is equal to actual impedance divided by base impedance. So we have discussed already this expression, that is Z by ZB. Here ZB nothing but which is the base impedance, which is the base impedance. So as already told, this base impedance can be expressed in terms of kV and MVA of base values. So much important one. So this base impedance is replaced with this expression, that is base impedance is equal to KVB square modulus of KVB square divided by modulus of MVA B. So finally you'll get Z per unit is equal to Z, that is actual value of impedance divided by KVB square into MVA. Here we should consider, that is, while substituting voltage and power, the voltage should be in kV, power should be substituted in MVA. So from these expressions we can conclude that this per unit impedance value is directly proportional to MVA of base value. Per unit value of impedance is directly proportional to MVA. So if you are feeling difficulties while remembering this formula directly, for remembering this final formula, if you are feeling any difficulties means, just you can remember by this simple expression while doing problems for finding per unit impedance. Simply write this formula and you have to remember this base impedance. You calculate base impedance using this formula and substitute these values in these simple equations. If you are feeling difficulties for remembering this final formula, you can proceed by the way I told. Next, some more per unit value expression for three-phase circuit. So these are the expression we have already seen. Apparent per unit power in polar form, which is equal to product of voltage in per unit into product of current in per unit with complex conjugate. And similarly, the voltage per unit value is equal to Z per unit value into I per unit value. For three phase, this apparent power is represented as S L three phase. So if you are taking the complex conjugate for this three phase power means you will get 3 times of single phase power. So this S per unit is equal to product of voltage and the complex conjugate of I. Here we are expressing SL complex conjugate. That means this VP carries complex conjugate and there is no complex conjugate for IP. So we know that the phase current is given by this VP and IP represents the phase values. So in this phase current represents VP divided by ZP and load impedance is equal to ZP, that is equal to VP divided by IP. So the load impedance, go through the previous slide. Here load impedance equal to VP divided by IP. So keep this VP as it is and substitute the expression for IP from this expression from SL complex conjugate of three phase. So IP is equal to this SL complex conjugate of three phase divided by 3 into VP complex conjugate. You substitute in the load impedance, so you will get this equation. Here this multiplication of VP along with the complex conjugate of VP, that is equal to 3 into modulus of VP square divided by SL star, that is SL complex conjugate of three phase. Next you can write root 3 into VP and root 3 into VP. You can write 3 as a root 3 into root 3. So you'll get root 3 into VP into root 3 into VP. So root 3 times of VP, that is root 3 2-3 times of base voltage is equal to 9 voltage if it is a star connected load. So finally you get V modulus of VLL square, that is line voltage and square, divided by complex conjugate of 3-phase power. So this formula is much important in problem. In rare case, instead of giving load impedance value directly, they will give the line voltage value as well as this apparent power for load. So you have to calculate actual load impedance value using this formula. In rare case only you will have this like this calculation. So you have to keep on remembering this one. So used to calculate actual load impedance value for 3-phase load. Next, the per unit impedance is given by, so already we know that load impedance in per unit is equal to actual value of load impedance divided by base value of load impedance. So same formula already we have seen. For a base value of impedance from kV and MVA, you can express as a ratio of kVb square and MVA-B. Both are base values because we are calculating base impedance. Next, this is a very much important concept, that is change of base. So you will be given some network for analysis in the problem. So they will give some base values, new base values. So you have to find per unit reactance network or impedance network of given power system network for those new given base values. So that means base values are changing. So while changing these base values, the per unit values of each equipment connected in the network also changes. That change in per unit value of each equipment or new per unit value of each equipment can be calculated by using the following final formula. To consider this derivation. So for any circuit element, the per unit impedance is expressed as the actual, this is ratio between the actual impedance and the base impedance. So already we know this. So here this base impedance is expressed as a ratio of kVb square, kV square and MVA. So finally you will get this formula. So as already told, per unit impedance is directly proportional to MVA. Next, consider that we have some per unit value for each equipment, per unit impedance value for each equipment in the network, which is to be considered as a given value. This given value means The per unit impedance value specified in the network or equipment is the given per unit impedance value. So we want to find out new per unit value for change of base values. So that new base values are denoted with subscript new. Subscript new is the new base values for MVA, and this is the new base value for KV. So they are represented with the subscript new. So from the given per unit impedance value, we want to calculate Z per unit new value. So the relationship already we have derived or given per unit value. To go through the previous slide, in which this per unit impedance equal to actual impedance divided by kV square into MVA. So for a given value, if you modify this, you will get Z per unit given. Only in the previous equation, just add subscript given. That's all. So Z per unit given is equal to Z actual divided by KVB square given into MVAB given. Next, so from this, find the expression for Z actual. So Z actual is equal to Z per unit given into KVB square given divided by MVAB given. So it's the expression for given per unit impedance. Similarly, you can write the equation for new impedance per unit value, that is Z per unit new. So that is equal to, here only change is it is a new value. So you can replace simply the subscript given in the subscript. You can replace this given with new. That's all. So Z per unit new is equal to, there is no change in the actual value. Actual value is same, which is given for any equipment. Actual values are not changing, only per unit values are changing because of change in the base values. Because we know that per unit value is equal to actual value divided by base value. So there is no change in actual value, only base is changing. So this actual and Z actual also the same value. So Z per unit new is equal to Z actual into KVB new square into MVAB new. So we want to get the expression for Z per unit in terms of Z per unit given. So you can substitute the expression for Z actual from the previous one. So substitute this Z actual in this equation, you will get Z per unit new is equal to Z per unit given into, so segregate this KVB and MVA ratios. So for easy remembering, so Z per unit given into KVB ratios with squared KVB ratios with squared into MVA ratios. So it will be somewhat difficult when you look at this formula during first time. I will give some idea to remember this formula. Just listen. So as already told, per unit values are directly proportional to MVA. Per unit values are directly proportional to MVA. So we are writing the expression for Z per unit of new value. Z per unit of new value. That means Z per unit new is directly proportional to MVA of new. MVA of new. That means in the expression MVA of MVA B of new will be in the numerator because Z per unit new is directly proportional to MVA B new. So automatically the given it comes in the denominator. MVA B given in the denominator. Here you will get with opposite manner. That is here in the MVA the given is in the denominator, but in KVB it will be in the opposite manner. Here the given is in the numerator and new is in the denominator. So you can remember by this ways. Once again I am repeating, Z per unit new is equal to Z per unit given into KVB ratio square into ratios of MVA B. So Z per unit new is directly proportional to MVA base new. So automatically given will be comes in denominator for MVA. For KVB ratios this will be in the opposite manner. So KVB given in the numerator and KVB new in the denominator. So after seeing some more concept, we will solve some problems. We will meet in the next session.